In this video, we'll talk about using our polar functions to now find areas of regions. Assume that we have r as a function of theta, with f theta bigger than 0 between two angles, and I want to find the area enclosed inside the graph and on that sector of angles. So what does this look like? Well, the picture is something like this. You've got your function, r as of theta out here, and I want to take two slices at angles alpha and beta, and I want to figure out this region inside here. And so we're trying to figure out what is the area of that region. That's the picture we're trying to think about here, is this is the area that I want to compute, the area inside a curve like this. If you look at these kinds of regions, and this one in particular, this will be really hard to find by any of our other methods we had so far. Right? This purple graph is not y as a function of x, and the region itself is neither vertically simple nor horizontally simple. This would be a very hard region to try to find the area of using normal Cartesian coordinates and normal techniques. That's why these polar functions help us out a lot, because they let us do this area without too much complication. How can we use this polar structure to calculate this area? Well, the main picture to have in mind here is the following, right? Remember, for Cartesian coordinates and areas under curves that way, we had the idea of if I had a function, I would chop it up into little pieces, add up the area of each piece, which was a rectangle, and then go to a limit to get the area as an integral, as a limit of Riemann sum. So what can we do here? Well, now we're thinking of theta now as our independent variable, and r as a dependent variable. So in Cartesian coordinates, x is our independent variable, and we found this area by splitting up x into tiny little pieces and then adding it from there. Since theta is now our independent variable, we're going to chop this up in little pieces of theta. Now the difference here is that when I take these little slices, I don't get rectangles anymore. If I take a small little slice of theta, this region that I get, this thing over here, is not a rectangle. It's more of a triangle or a circular sector than anything else. So to get to an integral to find this area, I need to figure out what is the area of one of those little sectors or little triangles, and then add all of those up to get my entire area. In this case, we want to figure out the area of each one of these little triangles, and that will give us a way to write an integral to find the area of this entire thing. So if I have a little sector, something like this, where my angle here is my change in theta. That's what it's going to be when we're setting up this sort of Riemann sum. How am I going to find the area of this shape? Well, we're going to approximate it by a triangle, and to do that I will then need this base and this height to give me what this area is going to be. So the base here is clearly just the radius r that we're at this point theta. That's the length from the base of this, which is at the origin, out to the edge of this curve. But what is the height? What is this length up here? Well, it turns out this is r times delta theta. That comes from either looking how this has to change as r gets bigger, right? If I take a slice down here, this length is smaller because it's closer and the r is smaller. But as r gets bigger, this goes the same way, and you should get r delta theta there. In addition, if you think about the circumference of a sector of a circle, r delta theta is what you get for that circumference as well. That's why the whole circumference is 2 pi r, because a full loop around the circle has delta theta of 2 pi. That formula works there as well. So the area here should then be 1/2 the base times the height, which is 1/2 r squared delta theta. Now we're going to add all these up, and then take a limit as delta thetas go to 0 to give us a Riemann sum, which will then convert into an integral, which gives us the following formula for the area inside a polar curve. So if f is a continuous function with f positive, then the area bounded by the polar curve r equals f of theta, and the rays theta equals alpha, theta equals beta, is given by an integral from alpha up to beta, like it should be normally, times our function for the area of each individual slice, which is 1/2 r squared d theta, or in terms of my function, it's integral from alpha to beta of 1/2 f of theta squared d theta. And that's how we find the area inside polar curves. Check this works. Let's look at a circle of radius r. If I take a circle of radius r, I can write that as the function f of theta equals r. That would give me the circle of radius r centered at the origin. Based on my formula here, the area should be the integral from 0 to 2 pi of 1/2 times r squared d theta, which just becomes 1/2 r squared theta from 0 to 2 pi, which is pi r squared. So this checks out. We get the answer we should for the area of a circle. Now it's important to think about how this actually gives us the area of this curve. And the point is, we're sweeping out the area sort of in a radial arc, as opposed to doing it straight horizontally. So in this case, we're taking our curve, and we're sort of sweeping out the area in arcs going this way, right? We sort of cover this little bit as we move along. As we're sweeping out the area, it's 1/2 r squared over this region as we're sweeping this out. This is in contrast to rectangular coordinates, where we have our same function thing, but we're sweeping out area now going directly horizontally as opposed to going in an arc. And that's important when you're trying to figure out how to find area of certain regions, is that the area below the curve before is now the area inside the curve that is between the curve and the origin, as opposed to being underneath it. Right? You're not doing area under curves, you're doing area inside the curve, meaning between the curve and the origin. We want to find the area of the portion of the circle r equals 2 cosine theta between the rays theta equals minus pi over 4 and theta equals pi over 4. So let's draw this out. If you convert that equation to rectangular coordinates, a circle of radius 1 centered at 1, 0. And if I draw on these two rays, it's a line up here and a line down here. The area I actually care about is this part in here. Now this area would be really hard to find in rectangular coordinates because it's not vertically simple, things are sort of weird. It's a lot easier to do using polar coordinates because we have a formula you can just write straight out right away and find this area. So our formula says this area should be the integral from minus pi over 4 to pi over 4 of 1/2 f of theta squared d theta, because the area I want is the part that's inside, that is between the origin and the curve 2 cosine theta. So I can write this out. I get a 1/2 out front, integral minus pi over 4 to pi over 4. My function is 2 cosine theta, so it becomes a 4 cosine squared theta. I can rewrite cosine squared as 1 plus cosine 2 theta over 2. That is my half angle formula. I'll get a 1/2, I'll get a 4, and then I'll get an integral from minus pi over 4 of 1 plus cosine of 2 theta over 2. All of my constants cancel out, and I can integrate this, and so I get theta plus sine of 2 theta over 2 from minus pi over 4 to pi over 4. Plugging this into my endpoints, I get a pi over 4 plus sine of pi over 2 minus a negative pi over 4 plus a sine of negative pi over 2 over 2. Since this is 1 and this is minus 1, what I end up with is a pi over 2 plus 1. And that's the area of that region. As you can see, it's much easier to do it this way than it would be to do it by any other method in rectangular coordinates, and polar coordinates let us simplify this out quite a bit. The point here is the formula was more complicated. Instead of just integrating a function, I integrate 1/2 the function squared. But because the function was a lot simpler in polar coordinates, we end up benefiting from that change to allow us to calculate this area. And that's where the real benefit comes in with these sort of ideas, is the function gets a lot simpler, which means you can actually work out these calculations where you may not have been able to otherwise if you wanted to use not polar coordinates to find these certain areas.